It's not just that it's mass versus volume. Notice that we're dividing by this either the volume of solution or the mass of solvent. So it's actually can be quite different. An obvious question is, why do we need this new unit, molality? And the reason is that the volume of a solution is subject to change with temperature. So everything expands with increasing temperature, and so your solution's volume will increase as you go from, say, 25 degrees to 50 degrees, which means that you're dividing by a bigger number, which means that molarity is actually not constant with temperature. So for precise work in physical chemistry, we actually prefer molality because the mass of solvent doesn't change with temperature, and so that means that the molality is not a function of temperature, which is convenient for things where we're changing the temperature. Okay, let's go ahead and do an example problem. In this example problem, we have an aqueous solution of methanol, and it's 1 molar. And the density is not much different from the density of water. It's just about the same to this precision. And we want to know the molality. So let's convert from molarity to molality. So we can write out the concentration. You can say we've got 1.0 moles of methanol, and I'll just abbreviate that MEOH, methanol, for every 1 liter of solution. And so we want to convert this to molality. And so for molality, we need to know moles per kilogram of solvent. So what we have to do is first figure out what the mass of the solution is, and then figure out how much of that mass is made up of water and not methanol. So we're going to have to subtract out the mass of methanol. So let's do those parts. So first, let's find the mass of solute. What's the mass of methanol in 1 liter of solution? So we know that in 1 liter of solution, we've got 1 mole of methanol. We want to convert that to mass. So we have a mass, we need the molar mass. And so if we add up methanol's structure, we know, let's go ahead and write down methanol's formula up here. So it's CH3OH. So we've got 12, we had 4 for the hydrogen and 16 for the oxygen. And so we get a molar mass of 32. So we get 32 grams of methanol for every 1 mole. So we can cancel that and get the mass, and we can see it's just 32 grams. Okay. So that's the mass of this 1 liter. That's how much of that mass in that solution is taken up by methanol. But what's the total mass of solution? So the mass of the solution as a whole, we can just get from the density of the solution as a whole. So we've got 1 liter. So if we multiply our mass by the density, we can convert from volume to mass. And we said the density was 1 kilogram for every 1 liter. So in this example, it's sort of trivial to end up that we have just 1 kilogram. So we've got 1,000 grams of solution. And since we have 1,000 grams of solution and 32 grams of methanol, we can just subtract to get the mass of water, the mass of the solvent. So it's just a total mass, 1,000 grams, minus the mass of the solute. So we can see that's 968 grams of water. So we've got the grams of water, and we can turn that into kilograms. And so we've got the moles of methanol divided by the kilograms of water. So let's do that in the next page. So we said we had 968, so 0.968 0.968 kilograms of water. So we can just divide that to get the molality. So we can see that that is equal to 1.03 molal. And notice we started off with a 1 molar solution. So we can see for solutions that are in water, which has a density of 1 kilogram per liter, and that aren't too concentrated, so we're not really subtracting off much of the mass of the solute, the molality and the molarity are very similar. At least in the first two sig figs, they're actually going to be identical. This won't always be true, so you should check to make sure before you make that approximation.